Hi everyone, in this video, I'm going to be going through the mechanism of biosynthesis of the tetrahydrocannabinolic acid and cannabinoid THCA and then CBDA. So these molecules may look very familiar to you. They are precursors to THC, which is the active ingredient in marijuana. And the way much of it is made may look familiar to you since you have been doing chemistry with some of the biosynthesis and some of the terpenes. Okay, so let's get started. So this is the DAM APP that Professor Pirrung talked about. Okay, and this DAM APP is it's called dimethyl allyl pyrophosphate. Okay, and it is the precursor to it's an isoprenoid precursor, right? So this is what makes a lot of this terpenes molecule. And the THC in cannabis, it's a terpenoid. It's not a fully a terpene, but it's a terpenoid. So the first step is you start with the dimethyl allyl pyrophosphate. And as you guys may have remember, phosphate is a great leaving group. Okay, so it leaves. Okay, so when the phosphate group leaves, what you make is this carbocation that you see right here. Okay, when the carbocation is formed, it's the reason, usually you think that primary carbocations are very unstable, you don't ever want it. However, because this primary carbocation is stabilized by the neighboring pi bond, it's extremely stable. So in the next step, what happens is the alkene of another PPP, right? So this is IPP, okay, which is just an isomer of the dimethyl allyl pyrophosphate, okay? It attacks the carbocation. Once it attacks the carbocation, it forms this, it exchanges the chain by five more carbon. Okay, so it makes this 10 carbon chain with this tertiary carbocation. Okay, and the next step is the base goes ahead and grabs the proton to make this GPP. Okay, so what happens is this GPP reacts with this olivitolic acid, okay, to form this this intermediate right here. So the way that works is it's may look very familiar to you. This is electrophilic aromatic substitution, okay, and you guys may know that electrophilic aromatic substitution, electron donating groups directs orthopara, whereas electron withdrawing group directs meta, right? For this particular olivitolic acid, you have two electron donating groups, okay, and they will attack from this carbon because they're both ortho to both of the donating group, right? So the way you could draw this mechanism is push down the electrons, the carbon, okay, not from this one, okay, push down the electrons, and this will go ahead and attack this carbon, and you have the nature's best leaving group, which is OPP, okay, that just leaves, okay, and then that forms this intermediate, okay. It may look very familiar. This is a common intermediate in electrophilic aromatic substitution that gets the carbocation is not very stable right there, so it wants to gain the aromaticity back. It goes ahead and grabs the proton, you reform the double bond, and gives you hydroxyl back, okay? So this forms cannabergolic acid, CBGA, okay? And the CBGA, what it does is this is from 8A chemistry where the alkene will grab the proton, okay? So there's two sides of the alkene, either this carbon or that carbon could grab the proton. If you have the proton be grabbed by the carbon right here, it creates the more stable tertiary carbocation, and that carbocation goes through a hydride shift, okay? And now this may look like very uncommon hydride shift too, because in all the organic chemistry class, you've seen hydride shifts where it's only the neighboring carbon that shifts, right? But in this particular case, because it's in the nature, nature does crazy chemistry, so you could actually perform a hydride shift to carbon to give you this carbocation. So now you may wonder, why did that carbocation go from tertiary to secondary? Okay, the reason being is this secondary carbocation, being benzylic, is actually more stable than the tertiary cation because of resonance. Okay, because of resonance. And after that, what happens is you get then you form this double bond will go attack that carbocation to cyclize and form the 6-member ring. Okay, and this may look very familiar to you, right? This looks like menthol, right? This is the biosynthesis of one of the, looks very similar to menthols, right? And this is the one biosynthesis that you've seen in Dr. Pirrung's class. Okay, so this is called, this particular molecule is laminin, right? This looks this looks almost like laminin, right? You see how that looks very close to laminin? Okay, so that's the next step. And after that, get rid of the carbocation, you have this oxygen on the ring, goes and attacks the carbocation, and it closes, making another ring to give you tetrahydrocannabinolic acid, okay, or THCA. Alternatively, instead of that oxygen attacking the carbocation, you could also have this chemistry performed where you just quench it. Yep, you just have a base. So you have this proton right here. You'll have a base that grabs the proton and quenches the carbocation to give you cannabinolic acid, or CBDA. Okay, so this is the biosynthesis of the precursor to THC. And as you could see, a lot of the reactions that are performed here that you've seen in chemistry, but a lot of them are more that you don't commonly see in synthetic chemistry, but you do see in nature, because these chemistries are being done in an enzyme pocket where the conditions are just right to make some of these things that nature, our body, could do, but we can't do it in lab.